Hi everyone, welcome to Power Plant Engineering 101 by me, Arjarn Tom, or just Mr. Tom. This is episode 11, and I try to do this in English to extend to international audience. And I'm sure that Thai students and all Thai engineers will have no problem at all understanding what I'm talking about. During our previous episode, we have discussed about basic thermal power plant cycle, how we turn water into steam and send the steam through the turbine to produce the work that in turn turn the generator to produce electricity, and how we turn the steam back to water once again to be pumped to the boiler. And in our previous episode 10, we we were talking about how to increase the efficiencies of the cycle. And one thing that we have learned was that we have to try to increase the TH high temperature. TH or high temperature would be the temperature where we supply the heat to the water to turn it into steam. And at the same time, we should try to decrease TL, the low temperature. TL is the temperature in the condenser where we uh, dissipate heat into the environment to turn the steam back to water to be pumped to the boiler once again. And for this episode, we will try to determine the values needed to calculate the thermal efficiency, to calculate the heat rate that we want. The heat rate very is very important value that we need to calculate, because the heat rate will determine how much coal that we need to provide in order to supply or provide enough heat to the water in order to get the certain amount of power that we need. Another important value would be the the specific steam consumption, or SSC. The specific steam consumption would enable us to determine how much water need to be circulated in the cycle, how many tons per hour of water that need to be circulated in the cycle. So we will try to do that in this episode. Okay, first this is just to recap. This is the basic cycle for thermal power plant. We call it Rankine cycle. I have already talked about this in a previous episode, so we'll not go through it again. And this is how we calculate the thermal efficiency of the plant, which is work net divided by QH. Work net is the net work that the plant will get is equal work produced by the turbine minus work that we need to put into the pump in order to increase the pressure of the water. or we can write it in the heat form. It would be equal to QH minus QL divided by QH. And this graph just shows the area of QH, QL, and worknet. Okay, in order to determine the formula for each volume, we first look at the first law dynamic of open system. When we have something uh, coming in the close the system like this and coming out of the system, we also will have heat coming in, going out, or work coming in, going out. But anyway, we can write a formula like this. S1 is the entropy, is one of the important property of water and or steam. The actually entropy, ENTHAPHY, is the amount of heat or energy that is ready to be used in the water or in the steam at that state. So we will have the entropy at state 1 coming in, right? And then we will have heat coming in and work coming in. If it is heat going out, the sign would be minus. If we have work, uh, if we have work going out, again the sign would be minus. But in general, we will write it as a plus. So we have energy coming in plus the heat that we put in or the work that we put in plus the potential energy of the system and the kinematic energy of the system will be equal to energy of the water and all steam that coming out at state 2 plus the potential energy at state 2 and kinematic energy at state 2. The unit that we will use would be kilojoule per kilogram. Kilojoule would be the unit of work, and kilogram is the mass of the water or the steam. So if we look at the boiler, okay, we have the water coming in at state 4. You can refer back to this graph or the picture of the power plant cycle that we have shown. Okay, for the boiler, the water would come in at state 4. So we have S4 plus QS is the heat that we supply to the boiler by way of burning coal, to provide the heat, and then we will get the steam coming out at state 1. So if we look at the formula, we will get entropy at point 4 or state 4 plus the heat that we're putting in will be equal to entropy or energy at state 1. So we will get HQ equal H1 minus H4. So if we know the status of the steam at point 1, if we know the pressure and we know the temperature which we can measure, we can determine the entropy, which is the property of the steam at that point. And again, we can measure the status of the water coming in. We can measure the pressure. We can measure the temperature, and with those two properties, we can determine by looking at the graph or the table, whatever that we will talk about it later. We can determine the entropy coming in at point 4. Then we would know how to calculate the amount of heat that we have to put in the boiler. Again, the unit would be kilojoule per kilogram. And then if we look at the turbine, after the steam coming out of the boiler at state 1, it will go through the turbine to expand, to provide work, to turn the generator to produce the electricity, etc. And the steam would come out of the turbine at state 2. So for the turbine process, we will, if it's for the ideal process, we will assume it would be isentropic process. Isentropic process means that the entropy will not change. The entropy at point 1 and entropy at point 2 will not change. Entropy is another property for water and steam. H is entropy, ENTHAPHY. S is entropy, ENTROPHY. And if you look at this graph, you can see that from point 1 that water that steam enters the turbine and comes out at point 2. You can see that the entropy will not change. This is the graph of temperature versus entropy. You can see that the entropy remain the same, but in actual turbine is not ideal. The entropy will increase a little bit, so 0.2 might be somewhere around here. But anyway, we can measure. If we know the temperature, the pressure, we can determine the entropy. So we can find the entropy and use it in the formula anyway. So for the turbine, we there is no heat exchanging, and we can neglect the potential energy and kinematic energy because the height of the turbine would not be changed, and the velocity of the fluid coming in and out of the turbine would be the same. So we can neglect the potential energy and kinematic energy, and we will get energy coming in the turbine as H1 entropy at point 1, and then we have to minus the work that going out to generate the electricity, and we will left with energy at point 2. So we can determine the work provided by the turbine Wt by H1 minus H2. Now we look at the condenser. The steam that coming into the condenser would be at state 2, and when the steam coming into the condenser, we will have QL out. QL would be heated that will be dissipated to the environment to turn the steam at state 2 into water or into liquid form at state 3. So again, if we can write the formula at the condenser, we will have H2 coming in minus QL going out, and we will left with entropy at S3. So if you want to determine how much QL that be dissipated into environment, we will get QL equal H2 minus H3. And for the pump, again, we will have after the water leaves the condenser, the water will uh, go through the pump at S3, and then we will provide work to the pump to pump the water up to the certain pressure that we want, which is the boiler pressure. So we will pump the water up to state 4. If we look at the formula, we will get H3 coming in plus work pump also coming in will be equal to S4. So if we want to determine how much work that we put into the pump, we will get WP equal S4 minus H3. Okay. If we assume the water to be incompressible fluid, it cannot be uh, compressed, we will get the specific volume of the water to be constant. Okay, and for the what we call reversible steady flow process, the change in entropy will be equal to the specific value multiplied by the change of the pressure, which is P4 minus P3. Okay. And we can write VP or work supplied to the pump by S4 minus S3 or equal V3 multiplied by P4 minus P3. And we want the unit to be kilojoule per kilogram to be consistent with the other values. So in order to do that, normally when we look at the the unit for specific volume in the graph or in the table, in the in the graph or in the water stream table, the unit will be cubic meter per kilogram, and the unit for pressure would be bar. So we need, in order to get the unit of kilojoule per kilogram, we will multiply by 10 to the fifth divided by 10 to the third. Okay, to just to make the unit consistent. So this is the formula for work pump, work provided to the pump. And after that, we will to be able to calculate the thermal efficiency, which is the work net divided by QH. Work net would be work that we get from the turbine, or work out minus work that we have to supply to the pump, which is work in, divided by QH. Or we can write it in terms of entropy. We will get work turbine would be H1 minus H2 minus work pump would be H4 minus H3 divided by QH, which is H1 minus H4. So if we can determine the entropy at point 1, 2, 3, 4, okay, point 1, 2, 3, 4, from the graph we can determine the thermal efficiency of the cycle or thermal efficiency of the plant. Okay, another, like I said, another important value that we need to determine is the specific steam consumption, or SSC. Specific steam consumption is the amount of steam that we in kilogram per hour that need to produce, give the work net of 1 kilowatt per hour. So the unit of specific steam volume would be kilogram per kilowatt hour. And we know that kilowatt hour is the unit of electricity, one unit of electricity if the kilowatt hour. So we could say that a specific steam consumption would be the amount of steam that needs to be in kilogram that needs to produce one unit of electricity. And to find the formula for SSC, the formula for SSC is 1 divided by worknet. This is and we want to get the unit in kilogram per kilowatt hour. So we have to do some calculation, and we get the formula for SSC equal to 3,600 divided by worknet. This is just to the 3,600 just to make the unit to be what we want it to be kilojoule per kilowatt hour, because if we just divide it by 1 by worknet, we will get the formula uh, kilo kilogram for kilojoule, which is not exactly what we want, but we know that 1 kilowatt is 1 kilojoule per second. So we can determine uh, we can change the kilojoule to kilowatt hour by multiply by 3,600. Okay, that's just not something to be worried about. Just to know that the formula for specific steam consumption is 3,600 divided by worknet. And maybe if we apply the turbine efficiency, we can multiply that here. But for the sake of just in general, we will assume that the efficiency of the turbine will be 100%. And what is saying here? And the SSC is important because we wa- can use SSC to determine how much water and or steam that need to be circulated in the cycle in terms of like ton per hour to get the megawatt of the electricity that we need. We can multiply by, megawatt of the electricity that we want to produce by SSC to get the ton of ton per hour of the water and all the steam that need to be circulated in the cycle. I will show you in an example in the next slides. And also another important value that we need to calculate is heat rate. Heat rate would be equal to QH divided by worknet multiplied by 3,600, and the unit of heat rate would be kilojoule per kilowatt hour. So the importance of the heat rate would be we can use the heat rate to determine how much coal that we need to provide in order to uh, give enough heat to the steam to produce electricity, the amount of electricity that we need. because the heat rate, the unit of heat rate will be kilojoule per kilowatt hour. That would say the amount of kilojoule, amount of heat that we need to produce 1 kilowatt hour or 1 unit of electricity. So if we for coal, they will have a coal will have a property called gross caloric volume. Sorry for or higher heating volume. Uh, that will say that how many kilojoule that they can produce per kilogram. So if we multiply that by the heat rate, we would know how many kilogram that we need to be supplied to the power plant. I will show that in the example later. So those would be the formula that we need. This just tell the benefits of doing that. We'll mainly the goal would be to increase the high temperature TS and to decrease the low temperature TL. Right? And another thing that we want to do is to reduce the amount of water droplets in the system, because the water droplets will be harmful to the turbine, and it can cause corrosion. So we will want to reduce the amount of the water droplets as much as possible. And anyway, the temperature that we can increase the TL would be limited to the material in the turbine, because we cannot just increase the temperature. We normally can increase the temperature up to like 500 degrees Celsius, something like that. Now we want to look at an example. This is the basic uh, I say the common uh, cycle that used in power plants in general, in thermal power plant in general. We will have superheated, and then the steam will go through the high pressure turbine, and then will be sent back to the boiler again to reheat, and then it will go through the second state turbine, or in this case low pressure turbine, to produce the work, and then the steam will go through condenser to be converted to the water again. If we look at this graph, the temperature versus the entropy, you can see that okay, from the water at state 5, if we pump to the boiler pressure, this is the pressure line, the pressure line. Okay, if you look at the graph of the temperature versus entropy, you can see that the pressure line will go like this. It will be somewhat horizontal in this dome here, but outside would be like this. So the water would be pumped to from 5 to 6 to this the boiler, we call it boiler pressure, and then it will be heated, up to this point number 1 here. You can see that this is the saturated vapor line, and if we continue heating the steam, it will go up to this point 1. This is the superheating area, and then the steam will go through high pressure turbine here to provide work, and then it will drop to point 2 here. at the saturated vapor line, and then it will be sent back to the boiler once again to reheat. So it will be reheated to this point number 3, reheated to this point number 3, and then it will go to the second state turbine or the low pressure turbine to produce more work until it and the steam will leave the second turbine at this point 4 at the saturated vapor line, and then it will go through condenser, and the heat will be dissipated, and the the vapor will be converted to liquid form again. This line is the saturated liquid line. At this point, we call it critical point. Is the point that divide the saturated liquid line from the saturated vapor line. Yeah. So the saturated vapor will be condensed or will be converted to saturated liquid at this point 5, and then will be pumped again to point 6, and it will be repeated like this in the circle. So we will use this model as an example to determine its value. This is just an explanation that I just explained. Okay, this is also just since now we have two stages of turbines and also two stages of heating. The formula for thermal efficiency will be something like this: work net divided by QH plus QR stand for reheating, or equal work that we get from high pressure turbine plus work that we get from low pressure turbine minus by work that we provided to the pump divided by QH plus QR. And if we expand the formula in terms of entropy, we can get something like this. And the specific steam consumption again would be 3,600 divided by work net. And this is the example that we are going to use to demonstrate how to find all the needed values for the thermal power plant cycle. This is this example is superheating and reheating cycle. You can see that we will heat the water until it's turned to steam at point 1. This is the in superheating area, and then the steam will go through the high pressure turbine, and then it will be reheated to this point 3, and then it will go through the second turbine or the low pressure turbine and expand to this point 3, point 4, sorry, and then it will go through the condenser and convert it to liquid at point 5, and then will be pumped to point 6 again. So this is the example of superheating and reheating cycle. And for all the properties such as temperature and pressure at each point, we can measure, and then we will use the pressure, the known pressure and temperature to find entropy or entropy. And I will show you the values from real thermal power plant. You can see that from this example, you can see that this is superheating. You can see the steam coming out of the boiler. We can measure the pressure. For this one is 141 bar, and we can measure the temperature. In this case, it's 525 degrees Celsius, and we can measure the amount of the water or the steam flowing in the system. This one is 138 kilogram per second. And you can see that the steam will go through the high pressure turbine and then go back to the boiler again to be reheated. After reheated, we can also measure the pressure. This is will be the lower pressure. The high pressure would be 141 bar. This is will be 33 bar, but it will be reheated to 500 and 536 degrees Celsius, and 115 kilogram per second is the amount of the steam that flowing in the system. And after reheated, it will go through in this case, they have immediate turbine, also low pressure turbine. But normally the steam would be reheated just one time, and it will go through both intermediate pressure turbine and low pressure turbine, and then the work will be go to the generator to generate the electricity, and then the steam will go through the condenser and be converted to liquid form. This one is the aerator that we or open feeder pump that we already explained in previous episode. This is the purpose is to uh, extract all the gases from the water, and then the water will be pumped again back to the the boiler. So the temperature, the pressure we can measure, and we will need to find the other properties such as entropy and entropy from from the 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 chart, the graph, or the table, whatever that we want to use. Okay, for this one, at point one, 500, 500 uh, degrees Celsius at 42 bar, we can find entropy at this point at 3,442.6 kilojoule per kilogram. We can look at the graph at 500 degrees Celsius and 42 bar or 4.2 megapascal. Okay, we can do that by look at the graph, look at what we call Maurer diagram. Okay, this 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 one is entropy in kilojoule per kilogram, and at this axis is entropy, also kilojoule per kilogram uh, degree Kelvin, and this line, those line are the pressure. It's a bit difficult to look at this graph, but if you have to, like, this is 500 degrees Celsius, and this is 4.2 megapascal. This graph is in megapascal, so 42 bar would be 4.2 megapascal. If you draw the line from 500 degrees Celsius, the the crossing between 4.2 megapascal and 500 degrees Celsius, can determine uh, the volume of the entropy, which is 3,442.6. But I didn't really get that number from this graph because it's quite difficult to see. And I can show you a graph that maybe much more clearer. This is from the internet. You can go find it degree here, and this one gives you in bar, so you can go 500 degrees Celsius, and this is 30, 40, right? 30, 40, 50. So 42 would be somewhere around here, and with 300, 500, 500 degrees Celsius, you get the entropy around 3,400. But like I said, that was not what I used to determine the value of entropy. What I use is the table. We can use the table. But nowadays there an application. There's a Excel sheet that put all these values in the application and in the Excel sheet. You just use lookup. And you just put in like temperature. You just put in pressure, and they will give you the amount of the entropy or entropy that you want. So at 500 degrees Celsius, right? And the at 4.2 megapascal or 42 bar, right? But in this table, they give you at 4 megapascal and 4.5 megapascal. So in order to get the value at 4.2 megapascal, we have to do some interpolation between 4 megapascal and 4.5. Anyway, if we do that, we will get the entropy uh, equal to 3,442.6 kilojoule per kilogram, and entropy equal 7.066 kilojoule per kilogram degree Kelvin. Okay, this is what I used when I taught the student more than 30 years ago, but I still using it. But like I said, nowadays they are applications, they are programs that people have done, in order for you to just put in the temperature and put in the pressure, and you will get the value that you need. Okay, this is how we determine. So we can get the entropy and entropy at point one, and the same time we can get the value at point two. This by doing the same thing. Okay, we can get the value at point three soon. As we know that we need entropy in the formula, so the idea here is to find entropy for each and every point in the cycle. We have entropy at point 1 H1. We have entropy at point 2 H2. We have entropy at point 3 H3. So we need to find entropy for point 4, 5, and 6. And you notice that point 4 is under this dome. It is what we call wet vapor region. It is mixed between water droplets or liquid water and vapor. It's not pure liquid or pure vapor. You can see this line is called saturated liquid line. Along this line and beyond here, it will be 100% liquid or water droplets. And along this line is called saturated vapor line. So at this line and beyond, it will be 100% vapor. But inside this dome here, it will be mixed between water droplets and vapor. So in order to find entropy here at this point, we need to do some calculation. And another thing that I would like to point out is that the process between 3 to 4, when the steam going in to the turbine and coming out of the turbine, it is called isentropic process. where the entropy uh, from point 3 and point 4 will be equal, or S3 will be equal to S4. You can see that it's a straight line coming down. No changes in entropy. So we know that S4 equal to S3. We know the value of S3, so we can determine the value at S4. We know S4, and then we can use that to find entropy or H4. Uh, as I said that entropy at point 4 S4 will be equal to entropy at point 3 S3, and will try to find entropy or S4 in the wet vapor region. In the wet vapor region, we have a formula to find entropy or entropy. The formula would be quite similar. For entropy, entropy at S4 will be equal to saturated entropy at point 4. Point 4 uh, means point at pressure 3.035. If you go back to this picture, is this pressure where the heat is dissipated to the environment, or uh, you can call it condenser pressure. Saturated liquid or at point 4 mean this point. And X4 is the amount of vapor divided by the amount of total mixture, which is vapor plus water droplets. And SFG is evaporated entropy. We have another table to determine those numbers. We call it saturated steam pressure table. You can see that the pressure 0.035 is equal to 3.5 kilopascal. So at this pressure, we can find the saturated entropy, which is equal to about 3.391, and also we can find the evaporated entropy. If we do some interpolation, it would be around 8.13. You can see that we have also values for entropy, but we cannot exactly find entropy because we need to find the amount of vapor in the mixture first, the X value, before we can use the formula to find the entropy for that. So we will use the entropy equation to find X. As you can see, if we substitute all the volumes in the formula, we can get the amount of X at point 4 is about 0.9898, almost 100%. If you can see in this picture, you can see that point 4 is very close to this line, which is a saturated vapor line. And I said along this line, it will be 100% vapor. So this is very close to this line. So as we found that the X volume here is equal to 0.9898, which is almost 1 or almost 100% vapor. When we get the value X, we can substitute in this equation for entropy. And for saturated entropy and evaporated entropy, we can also find from this table here. You can see that we can find saturated liquid entropy and evaporated entropy for the pressure 3.5 kilopascal or 0.035 bar. This is how I explain to the student how to get the number using the Moria diagram. We can do that also, but it would be much much easier to use the table. And as I said before, nowadays there are applications and there are programs. The people already printed in all the values, and you can just put in temperature, pressure, and then they will give you the the the, the entropy, the entropy. Now we get S4 and S5 and S6. We can do the same thing as before to get the number. So now we can find the thermal efficiency for this cycle here. Like work net is equal to S1 minus S4 plus S3 minus S4. No, S1 minus S2 plus S3 minus S4, which is the amount of work uh, given by high pressure turbine plus the amount of work that we get from the low pressure turbine minus H6 minus S5, which is the amount of work that we put into the pump divided by QH. It is uh, H1 minus H6 is the amount of heat that we put in along this line. Also, we have reheating. So QR would be equal to H3 minus H2. It is the amount of heat that we put in along this line. If we do the calculation, we will get about 41.22%. And I noted here that it's more than just the superheating cycle that we did before. Before this example, I did the just superheating cycle for the student and find the thermal efficiency, and we got 39.5%. And for the superheating and reheating cycle, we get 41.22%, which is better. And I also did an example for just basic cycle, no superheating, no reheating. We will get the thermal efficiency about 36.8%. So it is proof to us that with superheating and reheating, we can increase the thermal efficiency. We can also increase the efficiency for the specific steam consumption. For this example, we get the specific steam consumption about 2.13 kilogram per kilowatt hour, which is, for the previous example, which is superheating example, the SSC would be 2.72, meaning that we need more water, more steam to get the same amount of kilowatt hour. If we do the superheating and then also do the reheating, we get a better amount of specific steam consumption with this less. You can see that we use less water and less steam to get the same amount of kilowatt hour. And even comparing to the basic cycle, just basic cycle, no superheating, no reheating, the specific steam consumption would be a lot higher, 3.34 kilogram per kilowatt hour. So this is why we do the superheating, we do the reheating to improve the thermal efficiency to improve the specific steam consumption, and you can see that it will improve heat rate as well. So if we get if we get if we can if we calculate the steam specific consumption, what what that would do, that would tell us how much water that we and how much steam that we need to be circulated in the cycle. For example, if we know the uh, specific steam consumption, for example, in this example, 2.13 kilogram per kilowatt hour, and we want to build a plant that will generate 100 megawatt of power, then we can calculate the amount of water that needs to be circulated in that plant, in that thermal thermal power cycle, by multiplying 100 megawatt with 1000 kilowatt per megawatt. We have to uh, change from megawatt to kilowatt first, and then multiply by 2.13 kilowatt per kilogram per kilowatt. So in this example, if we want to generate 100 megawatt of power, we would need to circulate about 213 tons per hour of water and steam. So this specific steam consumption is quite important in order for us to know how much amount of water that we need. And another value that we need to find and calculate is the heat rate. Heat rate, the unit of heat rate is kilojoule per kilowatt hour. It tells us how much energy, how much kilojoule of energy that we need to produce 1 kilowatt hour, 1 unit of electricity. That is very, very important, because for that we will use that number to determine how much coal that we need to supply to the power plant, for example. So the formula for heat rate is QH divided by work net multiplied by 3600. Okay, if we use the number from my example here, uh, QH would be equal to 3326.4, and work net would be equal to 1689.3028. We multiply that by 3600. We get the heat rate for this example about 7088.75 kilojoule per kilowatt hour. It means that we need the heat from coal or from whatever fuel. 7088.75 kilojoule to produce the electricity 1 unit, or to produce the power of 1 kilowatt hour. So if we know the amount of kilowatt hour, or amount of the units of electricity that we need to produce per year. For example, if we know that this power plant need to produce or generate 100 gigawatt hour per year, or 100 times 1000 times 1000 kilowatt hour or unit per year. If and we know that if we know that the coal that we're going to use have the what we call the higher heat heating volume, or we can call it gross caloric volume, is the amount of heat that coal can give per kilogram. So if we know that the coal that we're going to use have this higher heating volume equal to 12,000 kilojoule per kilogram, which is quite uh, normal, or this is quite an average volume for coal. So we know that by doing some calculation, we can determine how much coal that we need to supply to the plant per year, which is in this case is about uh, 59,072.917 ton per year. So if we know the amount of coal that need to be supplied per year, we need to, if the concession or the period of the agreement or whatever is 30 years, we need to find a coal mine that have enough coal to supply to the power plant. So we have now we have done all the calculation to determine uh, important values in the thermal power plant cycle, or for thermal power plant we know now how to calculate all the values that need to be calculated. Okay, I think that should be uh, the end of this episode. Maybe next episode we can talk about specific issue concerning uh, thermal power plant, or power plant engineering in general. So for this episode, thank you for watching, and see you uh, in the next episode. Bye bye.